Let's look at the support vector machine as the sixth topic of machine learning. Support vector machine uses a constrained quadratic programming. To better understand the support vector machine, it is helpful to first understand the convex optimization, which we discussed in the previous topic. In this video, we will look at the linear hard margin algorithm of the support vector machine. A linear hard margin SVM is only possible if a straight line can completely separate two data clusters without error. This video was produced in Korean and translated into English. My voice was generated using AI, text-to-speech. Let's take a look at the full table of contents. There is quite a bit to learn about the support vector machine. Let's go through them step by step. Let's look at the classification and the regression using SVM. In the classification part, we will look at the linear and nonlinear SVMs. Let's look at the kernel trick in nonlinear SVM. And let's take a look at the multi-class classification. In the regression part, we will also look at the linear and nonlinear regression. When implementing SVM, we use the CVXUp library to solve the QP problem and calculate the decision function to predict the class of the test data. We will also implement SVM using scikit-learn's SVC and SVR. And let's compare the results of the two methods. Let's look at the best decision boundary. Let's consider the data distributed as shown below. The class Y of the red data points are +1, and the class Y of the blue data points are -1. There are countless decision boundaries that can distinguish these two clusters. The decision boundary of case A classifies the two data clusters well. And that of case B also classifies them well. Additionally, numerous decision boundaries are possible. Draw a random straight line between the two clusters and shift this line parallel to the left and right until it reaches the data, creating two straight lines. This data point and this data point where these two lines meet are called the support vector. The straight line that intersects the data point with the class of +1 is called the positive boundary. And the line that intersects the data point with the class of -1 is called the negative boundary. The best decision boundary is the one with the largest distance between the two boundaries. Support vector machine is an algorithm that finds the best decision boundary that can best separate two clusters. The distance between two boundaries is called margin. In other words, the support vector machine is an algorithm that finds the decision boundary that maximizes this margin. Case A has a large margin, but case B has a small margin. Therefore, the decision boundary of case A is better than that of case B. Next, let's look at the decision rule and constraints. In the figure below, the class Y of the red data points are +1, and the class Y of the blue data points are -1. The straight line 1 is the decision boundary, the line 2 is the positive boundary, and the line 3 is the negative boundary. Let's call this equation the decision boundary. And this data point and this data point are support vectors. Again, SVM is an algorithm that maximizes the distance between the straight lines 2 and 3. W is the normal vector of the decision boundary. The coefficients W1 and W2 are the components of the normal vector W. And U is a vector for an arbitrary data point. Let's look at the decision rule first. If the dot product of W and U vectors is greater than or equal to a constant C, then the class Y of that data point is positive 1. Otherwise, it is negative 1. In other words, if the magnitude of the U vector going in the direction of the W vector is greater than or equal to a certain number C, that data point is classified as positive 1. So we can create the following decision rule. Now we need to use the given data to determine the vector W and the intercept B. Next, let's create the constraints. The data points with class positive 1 satisfy this equation. This equation is a positive boundary where the decision boundary is shifted parallel to the right by k. And the data points with class negative 1 satisfy this equation. This equation is a negative boundary where the decision boundary is shifted parallel to the left by negative k. In the figure, all the red data points are above the positive boundary, and all the blue data points are below the negative boundary. Now let's divide both sides of this equation by k, and write W over k and B over k as W prime and B prime respectively. For example, these two expressions are the same. In this equation, W is 4, 6, and B is 8. In this equation, W prime is 2, 3, and B prime is 4. Therefore, we can estimate W prime and B prime instead of W and B. To simplify notation, we will denote W prime and B prime as W and B. Then these two expressions can be written as one expression like this. When y is positive 1, it becomes the above equation. And when y is negative 1, it becomes the below equation. This equation can be written as below. And the support vectors x satisfy this equation because they lie on the positive or negative boundary. Now let's create an objective function for SVM. First, let's find the distance between the two boundaries 2 and 3. This is the unit normal vector of the decision boundary. We then use two support vectors, x minus and x plus vectors, on the positive and negative boundaries. The x minus vector is a data point with class negative 1, and the x plus vector is a data point with class positive 1. The difference between the two vectors is this red vector. The distance d can be expressed as the dot product of this red vector and the unit w vector. This is the magnitude of the red vector going in the direction of the unit w vector. And the support vectors satisfy this equation. The x plus vector satisfies this equation because y is positive 1, and the x minus vector satisfies this equation because y is negative 1. In this formula, substitute 1 minus b for the x plus dot w, and minus 1 minus b for the x minus dot w. Then the distance d becomes like this. Maximize this distance. This is equivalent to minimizing the norm of vector w in the denominator. For mathematical convenience, we use 1/2 and the square, which becomes the objective function for the SVM. Next, let's look at the optimization problem of SVM. The goal is to minimize this objective function. There is one inequality constraint. This constraint means that data points where y is +1 are above the positive boundary, and data points where y is -1 are below the negative boundary. As you saw in the convex optimization video, the standard form of an inequality-constrained optimization problem is as follows. Let's express the optimization problem for SVM in standard form. The Lagrange primal function looks like this. Here, the lambda is the Lagrange multiplier and must be non-negative. And this part is the inequality constraint h of x. Differentiating this function with respect to w and b gives us the following results. Next, let's find the Lagrange dual function. Replace w in the primal function with this expression, which is w star. Then we get the following dual function. This equation can be summarized as follows. This constraint causes the last term to be 0. Then, the final dual function would be as follows. X and y are known values from the data. So this expression is a function of lambda only. To find the solution of the SVM, we first need to find the lambda that maximizes this dual function. Then the dual problem of SVM is a quadratic problem QP as follows. The objective function is to maximize this dual function, or minimize this function. And there are constraints as follows. As we saw in convex optimization, this problem can be solved using the CVXOpt library. We will look at the actual solution process in the next video. Next, let's check whether the lambda obtained from the dual function is the same as that from the primal function. This is called strong duality, and we just need to check whether this problem satisfies all KKT conditions. In general, the primal solution is greater than or equal to the dual solution. But if all KKT conditions are satisfied, the two solutions are equal. KKT conditions are as follows. For more information on this, please see this video on convex optimization. Our problem satisfies all the KKT conditions. The first condition is satisfied because we differentiate the primal function with respect to w and b and find w star and b star with slopes of 0. Let's check whether the second condition, complementary slackness, is satisfied. If x is outside the positive or negative boundary, the lambda is 0, so this condition is satisfied. If you implement the SVM in the later video, you will see that the lambdas become 0 in that case. When the data point x lies on the positive or negative boundary, the lambda is non-zero, but this part becomes 0, satisfying this condition. The third and fourth conditions are constraints, so they are satisfied. Since the dual function of SVM satisfies all the KKT conditions, the solution of the dual function is the same as the solution of the primal function. Lastly, let's look at the decision function. In the training stage, a decision function is created through the procedure below. And in the prediction stage, this decision function is used to estimate the class of the test data. Step 1 finds the lambda star, which is the solution to the dual function below. In step 2, we use the lambda star to find the W star through this equation. In step 3, we use the W star to find the B star. There are two ways to find B star as follows. The first is the method introduced by Christopher Bishop in this book. The support vectors satisfy this equation. Multiply both sides by y. Since y is either positive or negative 1, y squared is always 1. Then, this equation can be written as follows. From this equation, we can find B star as follows. Find B using the support vectors x and their corresponding y. Calculate the mean of B. This is the B star. You can also calculate B star using a single support vector. But for more reliable result, use the average. The second is the method introduced in Andrew Ng's lecture. Calculate B star using the two support vectors. The two support vectors satisfy this equation. The support vector with y equal to positive 1 satisfies this equation, and the support vector with y equal to negative 1 satisfies this equation. Add these two equations, and use the formula on the left to find the B star. Here, this expression means that among the data points where y is negative 1, Wx is the largest, that is, x is closest to the decision boundary. And this expression means that among the data points where y is positive 1, Wx is the smallest, that is, x is closest to the decision boundary. Now that the W star and B star have been determined, we can create the equation of the decision boundary as follows. This is the decision function. This is step 4. Step 5 is the step of predicting the test data. Put the test data into the decision function. If y hat is positive, it is classified as positive 1. And if it is negative, it is classified as negative 1. So far, we have looked at the basic algorithm of SVM for linear hard margin. In the next video, we will implement SVM by solving the QP problem of a dual function using the CVXOpt library.